far, what have we done in here? We've talked about sorting. We've talked about searching. Those are algorithmic problems that you guys probably already know about, okay? Knew about before you came in here on some level. Although obviously there's more subtlety once you start to take a look at it. Graphs are one of an idea that you probably have been exposed to. How many people here have taken the combinatorics class, the 301 bar? And how many people have not taken that? Okay, so most of you have taken it, AMS 301, which is our combinatorics and graph theory course. If not, you've probably seen graphs somewhere along the line, because graphs are really one of the real unifying themes of computer science, okay? And what I'm going to want to do today is start out by talking a little bit, get us familiar with the language of graphs. So this unit is going to be algorithms for graphs. How do we solve problems on graphs? The single most important thing to know about graphs, okay, if you ask me how do I work with graph algorithms, okay, sometimes I design my own clever graph algorithms. But designing clever graph algorithms is very hard, that very smart people do. And that's not me, okay? What I am very good at, and that I think it covers almost all the applications of graph algorithms in practice, is graphs and graph algorithms have been studied well enough that there's a bunch of famous problems on graphs that account for the vast majority of things you want to do with graphs, okay? It is very unlikely you're going to come in and say, oh, my application is completely weird. It is a new thing to do on graphs. People have been doing things on graphs since the beginning of, beginning of time, beginning of computer time, okay? And it's well defined what the problems are. The basic skill that is very important is learning to recognize when your problem is asking a question about graphs and what the name of that problem is. That is how you solve problems, and you seem smart when you work with graph algorithms for the most part. Okay, and so I'm going to try to develop that skill today. That skill is a relatively simple skill if you study the canonical questions of what you do with graphs. So what is a graph? A graph is, okay, here's the definition. A graph is made up of vertices and edges. Okay, it's a set of things called vertices, which somehow I always draw as points, and certain pairs of things that are identified as being pairs of things as entities. The pairs are edges, the points are vertices, and that is a graph. Any questions? Okay, it's a collection of vertices and then a set of either ordered or unordered pairs of those vertices that form the edges. Any questions? So what are examples in life where graphs come up? Okay? One canonical example of where graphs come up are road networks. What is a road network? Well, you know that a road goes between two places. Okay? Typically one city to another. A road leg. Okay? So we have our endpoints, represent towns or road junctions, pairs of which are connected by roads. The vertices are the junctions. The roads are the edges. Okay, what kind of algorithmic questions might you ask on a road network? What is the shortest path, right? I want to get out of Stony Brook and go to Montauk. Okay, that's nice. What's the fastest way to get there? The shortest way to get there is really a problem. What other questions on graphs, on road networks might someone ask? So one question would be, I want to see Long Island. Okay, I really want to see Long Island. What is the way that I can drive to visit on every road in New York, on Long Island? I want to take a Long Island road tour. Does everybody see that? I want to see every piece of asphalt in Long Island. That might be a road problem, right? What problem is it actually? To visit every road in Long Island. It's actually not the same thing. Visit, suppose I say I want to see every city. That may have been your original question, right? Let's come back here. How would I visit every city? Maybe I'd start like this, and I'd go here, and there, and come back home, right? That problem we said was traveling salesman problem, right? The other problem was, let's say you're a road inspector. Let's say you're a mailman. You want to deliver mail to everyone in Long Island, right? Where do the mailmen live? People have post offices, mailboxes along the road, right? So what does the postman have to do? Postman's got to drive by every road, make sure he visits everybody's house. Does everybody agree with that? So they'd want to visit every edge in the graph. Does anyone have a sense of what problem that is? If you want to visit every edge once, what is that called? Does anyone remember? Euler's cycle, right? That was sort of Eulerian cycle. That's another problem on graphs. The postman wants to worry about that. What might be another problem you might ask about on the road network? Okay? Let's say you're the highway department that maintains the highways on Long Island. You probably want to try to figure out what collection of highways can I can I take out of action to inconvenience the most people. Okay, that's what it seems to me every time I drive on the Long Island Railroad at night, right? There's certain questions of analyzing the road network for reliability. How many roads do I have to cut to disconnect the graph? Okay, that's a well-defined graph problem. Okay, motivation may not be very strong here, but that's a well-defined graph problem. Any questions? What about circuits, electronic circuits? Can electronic circuits be modeled as graphs? Again, when I see a circuit diagram like that, actually, how many people in the course of your study see a circuit diagram? You know, I've never seen a circuit diagram at all. Okay, a couple people. Anyway, you've got components, right? These components are wired together to form a computer, right? We could sort of view that the junctions between things are vertices. The edges represent electronic components. These are resistors. Those are capacitors, right? That is a graph problem. And there are a lot of graph analyses that electrical engineers will do. Kirchhoff's laws. Anyone ever heard of Kirchhoff's laws? In a physics class, right? Remember Kirchhoff's laws? Kirchhoff was a graph theorist, okay? At least we would claim him as a graph theorist, okay? Because those are really graph theory kinds of things. Find all the circuits in a graph. Any questions? Any other graph theory things that you might worry about if you're a circuit designer? Actually, there's lots of graph algorithms done on laying out circuits on circuit boards and testing them and trying to design, how to do it to minimize wire length and things like that. So CAD people are consumers of graph algorithms. Any other graphs that come to mind in real life? Any of you have ever encountered a graph in the course of your day-to-day existence recently? Anybody encountered a graph? I look around me, I see graphs all the time, okay? And we'll talk about the friendship graph a little bit later, okay? But once you learn to think about graphs, okay, you think about relationships in the world. What are graphs? Your schedule, Stony Brook's schedule of students is a graph. What is it? You've got one set of vertices that are students. You've got one set of vertices that are classes. There is an edge between every class and all the students in the graph, the class. Does everybody see that? That's one way of modeling how enrollments work, and it's sometimes a useful thing to do. Learning to recognize the graph is an important thing in life. Any questions? Also important is learning to recognize what flavors of a graph you have. So different graphs have different properties. Again, the two things to keep in mind for today. Graphs arise in applications, and graphs have certain properties. And learning to think about what property the graph has is an important thing. So what's an example of a flavor or a property of graph? One of the most important ones is whether a graph is directed. What is a directed graph? Okay, a graph is directed if, or a graph is, I think, undirected, if an edge from x to y implies that there is an edge from y to x also, right? Sometimes we have graphs where there are arrows on the edges. That arrow means it goes from one place to another. In an drawing of an undirected graph, we don't have arrows, right? Are road networks directed graphs or undirected graphs? You say undirected. The answer is it depends. Okay? The Long Island Expressway, okay, or big highways are undirected graphs. I think I agree with that, right? Because if the road goes from here to there, you can drive from Stony Brook to Montauk or from Montauk to Stony Brook, right? On the other hand, within cities, Manhattan is most definitely not an undirected graph. If you try to draw Manhattan thinking it's a directed graph, you have problems, right? Because certain roads go one way. A lot of roads in Manhattan are one way. Does everybody agree with that? So certain graphs are, in a world where roads are one way, you have a directed graph. In a road where the direction is always, you can go either way, it is an undirected graph. Any questions? Okay? When you take a graph theory course, usually graphs that are interesting are undirected graphs. But in practice, there's a lot of directed graphs out there. And the things you do to directed graphs are not the same thing as you do to undirected graphs. So when you see a graph, one of your first questions you say is, are you directed? Any questions? Okay. Was the circuit graph we looked at before, was that directed or undirected? The circuit diagram. Let's look at this thing here. Is this, go back here. Undirected or directed? I think it's undirected. I can't think of it. Although actually, are there things like diodes? What? Now sometimes in some interpretation, current sort of flows in a direction, right? I hadn't thought about that. I think there were things called diodes. Is that right? Back in the old, I mean, people have diodes, right? What did a diode do? It prevented current from flowing the other way, right? So sometimes, in fact, when you think about graphs, circuits, people will think of them as undirected graphs, and sometimes they'll be directed, okay? And what the meaning of that is depends upon, which is right depends upon what you want to do. You have to be aware of that kind of thing. Any other questions? We didn't come up with any other graphs. I guess it's, yet so far. So we'll look at some other ones later, some other applications. But okay, directed is important. What about weighted or unweighted? Okay? A graph we say is weighted if every edge is assigned a numerical value. Are road networks weighted or unweighted at graphs? Say weighted. I say it depends. Okay? What? Well, it depends what your problem is. If your problem is, can I get from here to Brooklyn? The length doesn't matter, right? Okay? If I'm the Long Island Railroad trying to systematically cut edges to frustrate people, okay? The roads don't have length, do they? Okay? So in sometimes problems, edges have natural weights, right? So what would be a natural weight for a road network problem? Well, when I would hear you say toll, okay, you're worried about how much it's going to cost you to get from here to there, right? You want the minimum cost way. You don't want to pay a dime to Uncle Sam, okay, for using the roads, okay? Now, you may have a different criteria. You were worried about the length, right? You didn't want to waste gas, okay? Okay, policeman concentration. He didn't want to get a ticket. What did you want to minimize? Traffic. Maybe as an issue of drive time. right? So does everybody see that if you want to figure out what's the best route, yes, this is a problem on a weighted graph, but what the weights are make a difference. Does everybody see that? There are different sets of weights that can be interesting. Sometimes you are given a weighted graph. Sometimes you are given an unweighted graph. Okay? Any questions about it? Some algorithmic problems we talk about will make sense on weighted graphs. Some won't. Or some will make sense on unweighted graphs. Any questions? So that's a thing to do. What other ones? We're also going to worry about sometimes there are funny edges in graphs. Could we imagine an edge from one place to itself? In the road network, is there ever an edge that goes from one vertex to itself, a point to itself? Like, yeah, what would that be? Maybe there's a loop road. That would be an edge that goes from a vertex to itself. Does that make sense? Sometimes it makes sense. Sometimes it doesn't. Okay? It's kind of weird to have an edge from a vertex to itself. But sometimes these things arise naturally. Okay? A loop road, I guess, would be an example of that. Okay? Sometimes they don't. Okay? We'll see other graphs later where that might be a different question. Sometimes, it's like the question of, is there a path to drive from me to myself? You know, I might have an edge that goes directly from myself. An edge from me to me is called a self-loop. There may also sometimes be more than one edge between two vertices. Can we have in the road network more than one edge between a pair of vertices? Is there any interpretation for that in the road network? Yeah. So one possibility is that if we have if we model it as a directed graph, this would be a construct in there. And that's a perfectly valid construct in a directed graph. I don't think that's what I consider to be weird. More weird, but sometimes arising, are two edges from A to B in the same direction. Does that ever happen? Are there ever two roads between two places? Yeah? Anyway, you have a place in mind? Well, there's a difference between routes and roads. Okay? Let's think about that for a second, because that's an important distinction. Let's look back at Long Island. Oh, sorry about that. Ooh. Note that there are, if you want to go between Stony Brook and Sag Harbor, are there two roads at any place between any point? But there's lots of ways to get to Sag Harbor. Right? Does everybody agree with that? Perhaps you're saying you want to create a graph where there's going to be a path, an edge between any pair of vertices. If there is a path between them, for every path between them. Now that's generally not a good idea. You could do it. Why might that not be a good idea? There's lots of different ways to get between Stony Brook and Sag Harbor, right? Let's say we had a road network that looked like this. Everybody see what it is? Everybody see that? It's sort of a split here. How many different ways are there to get from here, x to y? 2 to the something, right? You tell me you want a graph with 2 to the something something. That's a bad thing, right? Because that's large. But it's certainly fair to say that sometimes there are parallel roads between things. Okay? I know I encounter them. Okay? Any questions here? We say that, to get back to this thing, you should be aware when that happens. Okay? We say that a graph is simple if it has no self-loops and no multi-edges. Okay? What is good about simple graphs? Well, they're simpler to deal with. Okay? Often a program that will work on a simple graph will crash when you run it on a graph which has a self-loop or a multi-graph edge, right? You'll say, I don't know that's true. Well, when you write your graph algorithms, we'll see. Okay? It's often a lot trickier to deal with these kind of things. Sometimes they arise in applications. Sometimes the graph is inherently simple. Okay? And being aware of this distinction is important. Any questions? Let's look at a couple of other properties. Again, I go through a bunch of these in the book. What about, we say that there's a distinction between sparse and dense graphs. Here we have a vertex, a graph with 1, 2, 3, 4, 5, 6, 7 vertices. This one also has 7 vertices, right? But this one has almost every pair of edges connected. This one has very few edges. Does everybody agree with that? If I have an n-vertex graph, how many edges can there be in an n-vertex simple graph? If the graph is simple and it has n vertices, how many edges might it have? I'm here mumbling, but no real good answer. How many edges might, if I have a graph on n vertices, what's the most edges it can have? I hear n squared-ish. Why is it n squared-ish? You have n vertices. Each vertex has how many buddies? If it's simple, how many vertices could it be connected to? N minus 1, not n, if it's simple. Because the nth vertex is itself, right? And each edge is now being counted twice if it's an undirected graph, right? Because if I'm an edge from me to you, that's the same as the edge back and forth. Something that is quadratic is the number of potential edges. But many networks have a linear number of edges. Okay? Let's think about our road networks. Are road networks sparse or dense? Sparse means it has like a linear number of edges, very few number of edges. The number of edges is proportional to the number of cities. Dense is one where it's quadratic. Are road networks sparse or dense? Sparse. How many roads can possibly go out of a city or a junction? Right? Every road's got to go someplace, right? So long as cities exist on Earth and they're not, sort of in 3 dimensions floating around. You can't have that many connections from a particular place. Does everybody agree with that? A connection takes up a certain amount of area and angle. You just simply can't have that many roads emerging from any one place, right? How many roads emerge from the city? Probably no more than a dozen, okay, if you actually cut off New York City from the rest of the world. The degree of it is low. Road networks are sparse. Any questions about that? Okay. Any questions? Okay, so I encourage you to look in the book about some of these other descriptions of graphs, because it's interesting and important to know about. But I'd like to polish up by talking about, now that we have a vocabulary for graphs, is a particular graph that, again, I think about graphs when I look out. I'm constantly on the lookout for graphs. One graph that is an interesting graph is something that I will call the friendship graph. What is the friendship graph? Okay, it is where we have 2 vertices, where we have a vertex for every person, and an edge if any 2 people are friends. Okay? So if we look at this again, this is an old graph. I guess the joke in the book is better, because now I guess more current. But again, at this point, George Bush and Ronald Reagan were friends, right? At this point, this is really an old thing. Ronald Reagan and Nancy Reagan were friends. There were rumors at the time that Nancy Reagan and Ronald were friends, and Frank Sinatra were friends. Okay? So you can imagine a graph where for every vertex represents a person, and pairs of people who are friends are connected. Okay? Any questions about what the friendship graph is? Let's let's think a little bit about the friendship graph. You may think it's a silly thing, okay? But actually there's a whole area of research now on social networks, which is very important. Things like Friendster. Any of you guys, I guess you guys have MySpace and stuff like this, right? How many of you have pages in MySpace or something, or a similar? Okay, many of you. Do any of you link to your friends' pages? Okay, aren't you building a friendship graph, right? You are your MySpace page. That's my understanding of the world, right? And you have links to your friend's MySpace page. You are saying, what are you doing? Okay, this I don't know, but you're really building a friendship graph. Does everybody see that? There is a friendship graph implied in MySpace pages, correct? Is that a directed or an undirected graph? You say it's an undirected graph. An undirected graph would mean that if I was your friend, you were my friend, right? Isn't that what undirected means? Are MySpace pages directed graphs or undirected graphs? Okay, this thing, I don't know enough about MySpace. Somebody with a MySpace page, raise a hand. Okay? You. Okay? Is your page, when you link to your friends, they have to acknowledge it. So I can't just link to you and become your friend. You might say, no, I don't want Skiena as my friend, right? So under that regime, it is a undirected graph. Does everybody agree with that? So we would like to think that friendship means an undirected graph. Does everybody agree with that? Now, not all relationships are like that. The question of if I'm your friend, does that mean you're my friend? This is a question about directed versus undirected graphs. The friendship graph, we would like to think, is a undirected graph, right? If I'm your friend, you should be my friend. That's what friends are for, right? What about the herd of graph? Is the herd of graph, the vertices are people. There is an edge from I to J if I has herd of J. Is that a directed or an undirected graph? Directed, right? I've heard of Arnold Schwarzenegger. Arnold Schwarzenegger has not heard of Skiena. Okay? Does everybody agree with that? Okay? Unless he's gotten interested in algorithms or something like that lately. I don't have any evidence he's heard of Skiena. Okay? What about the had sex with graph? Okay? You have a pair of people. An edge, if X has had sex with Y. Is that a directed graph or an undirected graph? As far as I know, okay, these things, okay, that is an undirected graph. Is that right? Because if X has sex with Y, Y has sex with X. That's my understanding. Okay? If your understanding is different, I don't want to know about it. Okay? Any questions about that? Okay? Now, in the friendship graph, am I my own friend? Okay? Who here thinks they're their own friend? You think you're your own friend. Who here thinks you're not your own friend? Okay? This may be a touchy-feely question. But what is it really asking? It's asking, does the friendship graph have self-loops in it? Does everybody agree with that? So we're asking, is the friendship graph a simple graph? Okay? And certain algorithmic questions are going to be different if you allow these kind of self-loops or not. Okay? That gets at, is it simple or not? Are there going to be multiple edges between pairs of friends? Okay? Is it possible that there be more than one edge between them? Depending upon what you want to do, it might be simultaneous. There might be reasons why. Like, let's say I know them because I'm a friend of you because you're in my algorithms class. And I'm a friend with you because you're in my dorm. Okay? Perhaps there are reasons why you might model that with multiple edges, right? If each friendship represented something. But on MySpace, do we think that could I become your friend many times? Apparently not, right? MySpace wants a simple graph. Can I become my own friend in MySpace? MySpace wants a simple graph. Does everybody see that? What else can we think about with graphs? Okay? Once you've got the MySpace graph, One kind of fun game to play with it is the 6 degrees of separation graph. Okay? Am I a friend? So let's say, does George Bush have a MySpace page? You know, I don't know if we take a look at it. Right? George Bush is on MySpace, right? Now, he's not your friend, probably. But maybe he's a friend of some of your friends, right? One thing you are probably going to be interested in knowing is if we have here George Bush, and here we have you, okay, is there a path in the graph from one place to another? This is an interesting question, okay? It gets the whole 6 degrees of separation thing. Is it connected? Is the MySpace graph in one place? Is an interesting question, right? Is it the case that there are friends, you know, I don't know, maybe this is the group of people in Iceland who are busy MySpace users, and these are the people in America. Are there any friendships that span from Iceland to the United States, okay, or not? If it is, the whole graph is connected, right? These are the kind of things we might be interested in the friendship graph. Does everybody agree with that? Why might we be interested in the shortest path in a graph? Okay? Let's keep going here. Why might we want to know how close you are? Let's say that, sure, George Bush has a MySpace page. And you can say, hey, look at me. I am connected. There's a path from me to George Bush. If I need a favor done, if your path is of length 10, okay, do you have any clout with George Bush? Now you tell me that your uncle is Karl Rove, okay? He's a direct friend to George Bush, right? Now there is a very short path here. Now I know you've got some clout, okay? And I'd like to talk with you, okay? So the length of paths makes a difference. We're going to be interested in shortest paths for reasons like this. Any questions? Okay. Again, this is it connected. Who has the most friends? How would you measure who has the most friends? This is important on MySpace, isn't it? Right? People keep track of how many friends do you have, right? There's some artificial ways to make friends, I gather, probably, right? Okay? What are we talking about in a graph theory sense? We really want to know what is the degree of this vertex. Okay? That's the question of who has the most friends. Okay? Any questions? So a lot of these relationship things work out naturally to graph theoretic things. And learning to recognize it and talk the talk is an important part of walking the walk. Any questions? Okay. Good luck. Next class, we're going to look much more closely at data structures and algorithms for working on graphs. Thank you.